Today I'd like to talk about approximating functions with polynomials. Okay, let's say we have a function of x that happens to be equal to a constant called a sub 0. Well, such a function would essentially look like a horizontal line, assuming the function of x is the vertical axis and x is the horizontal axis. And the position of that horizontal line will be determined by a sub 0. Now, let's say instead that same function is equal to a sub 0 plus a1 x. Now, you can have a line of a given slope, okay, which can be displaced vertically also. It can also be a horizontal line, especially if a sub 1 equals 0. Okay, and now if we have it be equal to a sub 0 plus a1x plus a2x squared, now we can have a line that's curved. It can be curved either up or down, depending on whether or not a sub 2 is positive or negative. And if it goes to a sub 0 plus a1x plus a2x squared plus a3x cubed, okay, in addition to all of these above, it can be a line now with two curves, okay? And the general rule is the higher the polynomial, okay, the greater the number of curves you can have, and also the more capable you are of altering the shape of that curve. And so what this does is that it allows you to approximate functions, and the more you have, the more functions you can approximate, and the more closely you can approximate those functions. Incidentally, if you have essentially an infinite order polynomial, which would look like on and on and on, plus a to the n, x to the n, and that take the limit as n approaches infinity, this will now allow you to exactly represent just about any function. Okay, so let us keep this in mind, and we're going to change gears for a little bit and then get back to this. Okay, now suppose we had to find a function called f of u, okay, and the given conditions are that the fifth derivative of u, okay, in this case I'm going to call it f5 in parentheses of u, is equal to the fifth derivative, okay, at the point where u is equal to 0, okay, and that in addition, the fifth derivative of 0, the fourth derivative of that point where u equals 0, the third derivative of that point where u equals 0, the second derivative of the point where u equals 0, okay, the first derivative of a point where u equals 0, and the function of the point where u equals 0, those are all constants, okay, so we'll say that those are given. Okay, so in this case now, if I have the point where the fifth derivative of u is the point where is the same where the fifth derivative of the point where u equals 0, so what I want to do to find the fourth derivative, okay, it's going to be f4, okay, u, I'm basically just going to integrate that, okay, is equal to the integral of the fifth derivative, okay, of a point where of u du, which is equal to, okay, mind you, these are all constants, as I said, okay, is equal to we'll call it f5 0, I'm just shortening it for the fifth derivative at the point where I equals 0, okay, times u plus f4, okay, 0, okay. So now we have the formula for the fourth derivative of u, okay, and on the next one I'm going to flip these orders, okay. So now the third derivative of u now is going to be equal to the integral of the fourth derivative of u du, which is equal to, okay, in this case it's going to be f5 0, okay, u squared over 2 plus f4 0 times u plus f, which is the third derivative of 0, okay. I'm just going to keep integrating that, okay. So now if I want the second derivative, okay, of u, that's going to be the integral, okay, of f3 u du, which is equal to, in this case, okay, f5 0 u cubed over 2 times 3 plus f4 0 u squared over 2 plus third derivative 0 times u plus, okay, second derivative of 0, okay. So now I'm going to find the first derivative, okay, is equal to the integral of the second derivative of u du, which is equal to, now that's equal to the f5 0 u to the fourth over 2 times 3 times 4 plus f4 0 u cubed over 2 times 3 plus f triple prime 0 u squared over 2, and mind you that's a fifth derivative, fourth, third, plus f double prime 0 u plus f prime 0. And so now to get the function of u, which is what we've been looking for, okay, we can say now f of u is equal to, okay, the integral of f prime u du, which is equal to f5 0, okay, u to the fifth over 2 times 3 times 4 times 5 plus f to the 4 0 u to the fourth over 2 times 3 times 4 plus f, okay, 3 0 u cubed over 2 times 3 plus f dot prime 0 u squared over 2 plus f prime 0 times u plus f prime plus f of 0. Okay, so now if we notice, if we just multiply those by 1, it doesn't change anything in the denominator, but we know that this is 5 factorial, that's 4 factorial, that's 3 factorial, that's 2 factorial, and that's obviously 1 factorial, which is equal to 1. So now, I just chose 5 to illustrate a point, and the point is that if we had taken the nth derivative, okay, so if we had given the nth derivative of f of u, okay, given the nth derivative of the point where u equals 0, and given all the derivatives, okay, down to the function as initial conditions, with all those being constants, okay, then we can see that in this case, f of u is equal to, okay, in this case, f of 0 plus f prime 0 u plus f double prime 0 u squared over 2 plus on and on and on, plus f to the n, okay, and in this case that's the nth derivative, okay, of 0 times u to the n over n factorial. Okay, now the important thing with this now is that the f0, f prime 0, etc., those are all constants. And the 2 factorial, the 3 factorial, 4 factorial, 5 factorial, up to n factorial, those are all constants. Constant divided by constant gives a constant. So essentially what this is that this is a polynomial, okay, which means we can use this now to estimate any function, okay, provided that we can find the derivatives, okay. And if we want to get it exactly, I simply put this in parentheses and take the limit as n approaches infinity, okay. So let's go ahead and do an example, okay, to illustrate what I mean. Okay, so in this case, okay, let's say now we have f of u is equal to e to the u, okay. So we know that f prime u is equal to e to the u, etc. Regardless, f double prime is equal to u is equal to e to the u. So now, if we take the point where u equals 0, then we know that f of 0 equals 1, f prime 0 equals 1, f double prime 0 equals 1, etc. Okay, so now using this formula that we just derived, we're going to find the formula for representing, okay, e to the u as a polynomial. Okay, so in this case now, it will be e to the u is equal to, well, f of 0, okay, in this case, e to the 0 equals 1, okay, plus, okay, well, those are all going to be 1. So it's going to be u plus u squared over 2 factorial, etc. Plus, okay, u plus u squared over 2 factorial plus u cubed over 3 factorial plus on and on and on, okay, plus u to the n over n factorial, okay? And we know that this is equal to e to the n because if we take the derivative of this, that goes to 0, that becomes 1, that becomes u, this becomes u squared over 2 factorial, okay? So basically we just shifted the whole thing right, and we wind up getting that the same number, okay? So we know that that works, okay? And this method of doing it, okay, or how it's represented, is called a Taylor series, okay, or sometimes called a Taylor expansion. And this is very useful because by breaking everything down into polynomials, which are very easy to integrate, it allows us to integrate functions that are very difficult or sometimes impossible to integrate otherwise. In addition, it also makes it easier to differentiate, and also easier to, for example, to use it in many different algorithms. In addition, if you notice, it's divided by the factorial of the number, so as the order gets higher, the denominator gets bigger and bigger, which means that if we just want a rough estimate, we can ignore many of the higher order numbers because we know those numbers are going to be tiny because they have such a huge denominator. Okay, so now with that in mind, okay, we're going to look for a more general term of this, okay? And in this case, we're going to pick another variable called x, okay, where x minus a is equal to u, which also implies that x is equal to u plus a, okay? So now, if I have this equation here, which I'm just going to write out again, okay, which is f of u is equal to, okay, the limit as n approaches infinity, okay, f of 0 plus f prime 0 u plus f double prime 0 u squared over 2 plus f triple prime 0 u cubed over 3 factorial. By the way, 2 is also equal to 2 factorial, plus on and on, plus n derivative of 0 times u to the n over n factorial. So now, let's have a more general term for this, okay? Because sometimes we have to pick cases where the initial condition is a condition other than 0, okay? So in this case, x minus a equals u, and x equals u plus a, okay? So if u equals 0, okay, at that point, the initial condition is going to be where x is equal to a, okay? So in this case now, f of x is equal to limit, again, as n approaches infinity. Now in this case, as we said, x equals u plus a. So if u equals 0 here, it's going to be f of a, okay, plus f prime a, okay, and u is equal to x minus a. So it's going to be x minus a. So wherever I see u, I'm going to substitute an x minus a, plus f double prime a, okay, x minus a squared over 2 factorial, plus f triple prime a, okay, x minus a cubed over 3 factorial, plus on and on and on, plus the nth derivative of a, x minus a to the n, okay, over n factorial. And this is the most general term for what we call the Taylor expansion, which is very useful, as I said before, in finding the integrals of functions which are very difficult to integrate. Anyway, that is all I have, and I'd like to thank you very much for watching.